Hello viewers and welcome to another episode of Space Science. Now you see there is no coding tutorial today, also the title indicates the word Python is missing. I'll be talking today about active asteroids, and this is some kind of format that will fit into this concept videos I uploaded a few weeks ago, like for example the part about reference frames or orbital elements and so on. And I was thinking to add some more scientific content on this YouTube channel, but not with some fancy animations or visualizations, but really guiding you through some actual papers that have been published so that you can understand what's going on in there. So really taking a particular paper, reading through it, or at least showing you the essence of the content. Of course, the papers I will show you are always freely available. So like this one, today it's about active asteroids, and the link to this paper is also in the description. Please let me know what you think about this format, whether it fits to the YouTube channel, whether it makes sense to have some additional content about science in general or space science in general. I'd really like to see what you think about this. So just write me a mail, write me something on Twitter or here in the comments. Now, before we start, one thing is very important, and this is something I always experience when I talk with other people, especially in the machine learning community or so, talking about papers, that everybody nowadays uses the word paper as a synonym for any kind of publication that's out there. And I think this is not quite fair, because a proper paper is being reviewed. So there are some smart guys, some smart scientists creating some content. They create their publication, a draft, and they send it to an editor, to a publication, and they send it to other scientists to review the content, to check whether it makes sense what's in there. They're sending back their comments to adjust the paper a little bit, and at the end of the day, you have some kind of iterative process that increases the overall quality of the publication. And nowadays, the word paper is used for basically anything, even for small blogs or so, or anything on archive. I know this paper is also part of or is accessible on archive, but it's always important to see whether or where the paper is actually being published. If it's a pure archive article, then it's more like a preprint, or if somebody from some but from some company is publishing something, it's also not a paper when it's not really reviewed. It's then something like, let's say call it publication, let's call it some technical description or so. Because it's writing an actual or publishing an actual scientific paper involves a lot of work, not only by creating it, but also through the review process. Now, enough with all the discussions about papers. Let's dive into a new topic, especially here about active asteroids. This is the first topic I choose, and I would like to go a little bit through it. We talked in the last Python sessions, we talked about asteroids, about this stony minor objects in the solar system. We talked about comets, the dirty ice balls that evaporate gas, and then dust is being ejected into the interplanetary space. And we also discussed that the dynamics of a comet, especially comets like the so-called Jupiter family comets, or also comets that have a larger period around the sun, they have a little bit different astrodynamical properties than asteroids. You may remember the so-called Tisserand parameter that is also being shown here in the introduction, TJ, the Tisserand parameter. That is mentioned here, and they write in this paper that, for example, main belt asteroids, you see it here, they have a semi-major axis that is smaller than Jupiter and a Tisserand parameter larger than 3, while comets that are dynamically linked to, for example, Jupiter, have mostly a Tisserand parameter smaller than 3. But somehow there are other objects in our solar system that behave weirdly. They appear to have some kind of cometary activities, but from a dynamical perspective, they remind one more of an asteroid. Yeah, so there is some kind of hybrid species out there that's neither asteroid nor comet. It's, yeah, we call it active asteroid. Now here there's some introduction. They also say here, they show here the on the small graph on the left side, figure 1, actually like this one where you have the Tisserand parameter on the x-axis and something just simply called activity on the y-axis. And this is what we just mentioned, right? We have here a region of so-called the Jupiter family comets between 2 and 3 Tisserand parameter with a coma, so they are quite active objects that are associated with some comets. We have also asteroids here in the bottom right with a Tisserand parameter larger than 3 with no coma and so on. But there are objects with a Tisserand parameter larger than 3 and with a coma called active asteroids. Of course, you can say, wait a second, astrodynamical properties, yeah, some Tisserand parameter, nice to have this one, but maybe it's just a comet that's those dynamical properties just change. Well, could be, but we will see that the dynamic or the reason why these objects are active, there's a quite large variety of reasons. Here on the right hand side you see some examples of active asteroids shown here as dark dots. So we have here the semi-major axis again on the x-axis and the eccentricity on the y-axis, and then you see a lot of different scatter points. Yeah, here the asteroids on the bottom, and then the black dots that indicate the currently known active asteroids. And one, I would say commonly, I don't want to say commonly known because it's maybe not known for everyone, but in the space scientific community, a commonly known active asteroid is especially this one here, 3200 Phaeton. Now 3300 Phaeton is an asteroid or active asteroid that is coming quite close to the sun. It also has some kind of activity because we see some remnants of Phaeton, namely the Geminid meteor shower in December. And also to understand the nature of Phaeton, the Japanese space agency JAXA will send a probe in a few years to this active asteroid. Now here in this paper they're describing some examples of these asteroids, and here in section 2 they show the currently known active asteroid, like for example, as I mentioned, Phaeton. So you can go through, for example, this column here where they list all the different publications that we're talking about or that were investigating Phaeton and so on. We have here a few images of, for example, Phaeton with some from some camera where you see some kind of activity around it here between 2009 and 2012. And on the right column, so papers are mostly two-column, written in two-column style, we have the next active asteroid called Pan-STARRS or 311P Pan-STARRS that shows not only a coma here in the center, but also different tails in different directions that are indicated here with some letters like A, B, C and so on for different dates, the 10th of September and the 23rd of September 2013. Now they are describing a little bit also the mechanism, what's behind it, what is the possible radius of the nuclei with an error margin also. So for example here they assume some kind of albedo. So the albedo is like the value, a dimensionless value that indicates how many % of the incoming light is being reflected. And based on the assumed albedo, often they assume a radius of Pan-STARRS, here in our case with 240 plus minus 40 meters. Now, again here, they are showing a lot of different active asteroids, examples, linear. We have here also series. This is a very nice image of P2010A2, which reminds a little bit of a cross, like an X or so. And the reasons behind all these different activities, we will show it in a few moments. Now let's go a little bit further, more examples here. I think also when there are like hundreds of examples, it becomes quite difficult to describe or to dedicate an asteroid on each side. I think this will be really difficult, but for now, this is a very rather new field that's quite interesting. Okay, so let's skip a little bit the asteroids here. We see a lot of images, a lot of activity is going on. Now, how many asteroids did they mention? I think now here in total 18. Yeah, so the last one is this Wilson-Harrington asteroid, active asteroid. Okay, so this is like the part that was describing the active asteroids, and that there are, from a dynamical perspective, there are some kind of weird objects that are associated with this, let's say, new class. And now they are describing here in the summarizing paper or publication the mechanisms behind these asteroids. And now, before we dive a little bit in, I will switch to some kind of draw. I will draw a little bit to explain it a little bit more. So don't worry, we will not stick only to this paper itself. Now, the first thing is the so-called rotational mass loss. Now, the rotational mass loss, before we check the equations, let's take a look at the, here are my notes. Thank you again. Let's take a look at the rotational loss. So let's pick up a color of an asteroid, like a gray color or something. And if we have our asteroid, which is like weirdly shaped in a way, it of course has some kind of rotational axis. Let's say like our Earth, yeah. So like here's the North Pole, and then at some point here's the South Pole, and it rotates here in our case, let's say anti-clockwise. If you take a look from the top. Now, of course, due to the rotation, we have here, the part here close to the rotational axis, which is where the velocity here on the surface is quite small. But we have also here somewhere the equator, or let's say the equator of the asteroid, and of course the distance here is, or the distance is being covered in the same time period, and of course the velocity here is a little bit way higher than at the poles. So, and if the rotational speed is so high that the centrifugal force are higher than the gravitational force of the asteroid, some parts can really fly away. So they are not really attached anymore to the asteroid, and they are then flying away to the outer space if the velocity is higher than if the escape velocity is higher than the when the particles reach the escape velocity, then they are not attracted anymore by the asteroid, or not sufficiently attracted anymore, and then they leave the surface and also the vicinity of the asteroid, making it in a way active. So this is a quite simple mechanism you can, I think, understand, right? You just rotate the object faster and faster and faster, and at some point at the equator or also other longitudes, material is leaving the object. So this is like the first case that is described here, the rotational mass loss. And for the rotational mass loss, they have an equation that is simply called the critical period, that is shown here in this equation. And it simply has some constants, 3 pi divided by the gravitational constant, and then here with rho, which is the density of the object. So you see there's no no value for the radius or so. It's really just the density computing then the critical period. And here they provide also a small example. They say that, for example, for a 1,000 kilogram per cubic meter dense object, the critical period is 3.3 hours. So yeah, if the object has a period of 3.3 hours, material is leaving the surface. And yeah, so you can then compute if you like, corresponding sizes and see what's the velocity, for example, at the equator. Okay, so they describe also some effects, how, for example, how an asteroid can rotate faster and faster. There are some different effects, but we will not cover them today. So here we have one example also from some Saturnian moon called Atlas, where you see here the region, the equator. It looks a little bit like a UFO or like a small, yeah, I don't know, has a bean shape, and you see here a lot of material along the equator, and if the velocity is high enough, material will eventually escape the object and is being then part of the Saturnian system. Okay, so the next part is also, I would say, quite trivial. It's the impacts. So really smaller objects impacting the active asteroid surface and then causing ejecta that then have a high velocity, larger than the escape velocity, and then they fly also into the into space. So you remember, for example, this X-shaped asteroid. This was actually a case where there were some collisions of some asteroids, probably causing this catastrophic event. And yeah, the distribution follows some kind of power law. So yeah, we don't have to dive too much into detail, but this is the second mechanism, the impact. And you see here, from a theoretical point, a lot of things have been understood. The third point is the thermal disintegration. So here on the right side, the next column, thermal disintegration is a little bit like, not the same like the comets, but in a similar way. You have different materials that form this asteroid, and of course, if you approach the sun closely and then you leave the sun's vicinity and then you come closer and so on, you cause a lot of stress to the material. So the material can crack. With cracking, material can then, of course, also evaporate, or other materials or other minerals are being then exposed, for example, to higher temperatures, also maybe causing some kind of outgassing. So, of course, this is the case when you have an orbit that causes this kind of different of thermal stress. So, for example, if you have here like the sun, for example, now this is a ugly sun. Let's make it a little bit more beautiful. Okay, still bad. And we have some kind of orbit that's, for example, very elliptic. Yeah, so the asteroid is revolving on such an orbit here. Here's the asteroid. When it comes closer and closer to the sun, it of course heats up, and then at the end it's cooling again. Then it heats up, cools, heats up, and cools. And this kind of material stress is causing cracks, fractures, and so on, and then also leading eventually to material loss. So Phaeton, for example, has also some, a little bit in a centric orbit where the surface, I think, can heat up to, I don't know, 300, 400, 500 degrees Celsius. So I'm not 100% sure, but Phaeton is just one case. You see here, among the active asteroids, here in this section, among the active asteroids, the most convincing evidence for thermal disintegration is Phaeton, also with the corresponding references. And It's even worse. So they say that the heating is up to 1,000 Kelvin at perihelion. So this corresponds to like 700 degrees Celsius. So it's quite a high temperature. Of course, the fourth point is sublimation of ice. So this gives a little bit a relation to comets. Yeah, so we don't have to dive into too much into detail here, but it's like simply, ice that is being sublimating. And now let's go to the last 2 points that are also, I would say, very interesting. For example, here 3.5 radiation pressure sweeping. That's quite interesting. It simply says that particles lifted above the surface of an asteroid are susceptible to solar radiation pressure and, if sufficiently small, can be blown away. So it's like literally the sun wind, that is just blowing away some dust particles. And you see here, and as an example, at around 3 AU, so 3 times the distance between the sun and Earth, 1 micrometer radius grain detached from the surface can be blown away from a non-rotating asteroid of 1 kilometer radius. And it also says by any process. So, for example, collisions or thermal cracking or whatsoever, if the 1 micrometer particle is being ejected from the surface, it is immediately blown away from the solar wind, because asteroid does not have any protective magnetic field or atmosphere, so it's just being blown away. And if this particle, for example, has a very small initial velocity, smaller than the escape velocity, it still doesn't matter. It is then carried away by sun's radiation pressure. Okay, the last thing, electrostatics and gardening, is something I would say it's for me personally, it's the most interesting part, because I would like to draw you here an example what this kind of mechanism is all about. So let's zoom into the surface of our asteroid. So we have an asteroid or also other objects. So we have also observed this effect I'm describing to you now also on the moon surface. And we have here the curvature of the asteroid or the moon or whatsoever. We have, of course, some kind of sunlight here from the left side illuminating the surface of the asteroid. And now, if you're a little bit familiar with quantum physics, you may know that, for example, ultraviolet radiation, when it reaches here some particle, it is being absorbed, and the energy goes to an electron, and the electron leaves the material, leaves the atom, charging or leaving the atoms in a positive charge. So what happens is that the electrons are, leaving, the surface, and the surface and also the dust is charged positively. So we have a small charge here of, if I recall it correctly, it was a few volts or so. So it's kind of significant. On the dark side, we have negative charge. So let's imagine we have here somewhere the so-called termination. So like the line dusk and dawn, where we have here negative charge. So it's somewhere here. And now imagine, let's zoom into the left part on the surface. Let's zoom into a small particle, a small dust particle that's there. Like we have here, let's put it on the top left. We have here our surface, and we have here our large dust grain. This dust grain is, of course, also positively charged, as well as the surface, which means, if they are not really attached in a way, but it's like a loose surface, this particle, this dust particle is, of course, lifting up. So it goes up. Now I just want to draw something. Come on. So it goes up. And if you have here, if it's close, for example, at the terminator, so between the sun illuminated side and the dark side, we have also some kind of potential between the sun illuminated side and the night side. So particles are then being accelerated like in a particle accelerator from the one side to the other, either, yeah, for example, to the top here, like in the small case on the top left, or then also accelerated to the other side, to the dark side. And if the velocity is high enough, of course, this particle will leave the vicinity of the object. And this effect has been observed actually on the moon. I'm not sure whether it was in what wavelength, but this was observed that there is some kind of, I don't know, let's be careful, dust haze or something. So this is the last interesting effect, this electrostatic effect here. So they also say here in the very first sentence that dielectric surfaces exposed to the ionizing UV and X-ray light from solar radiation develop a positive electrical potential, perhaps something between 5 to 10 volts, through the loss of photoelectrons. So you can go a little bit through here. There are also the references. They also say here that on the moon we have this horizon glow, for example, and also they say that near the terminator, so between the sun, the night and the day side, around 10 micrometers sized dust particles are lifted up to a meter or so, and also being accelerated. Yeah, this was the mechanics of this of the active asteroids. They also describe later some kind of diagnostic, some kinds of ways how to observe it, other distributions, also the dynamics of the objects as well as surveys and so on, and then leading to the summary of the paper as well as all the references that were addressed in this paper. So you see here, as it always says, science is like built on the shoulder of giants. And of course, in this case here, this paper, this publication contains a lot of references. So in this case here, I'm switching between paper and publication, I know. This is a part of a book, I think from a book called Asteroids 4, so the 4th edition of a book that was describing asteroids and so on. And so it's also being reviewed. And this was everything I wanted to show you today about active asteroids. So if you like what I showed you today, again, there's no fancy animation, just simply the plain text and using a pen and paper and understand what's in there. If you liked it, just reach out to me. If you have other scientific publications from the solar system or so you would like to know better, just write it into the comments. I have tons of other papers that I would like to show you, also from some spacecraft missions and so on. But yeah, of course, on the weekend there will be a new video about the machine learning project using Python. I hope you enjoyed it, and until next time.